All right, we are at section 32.4, capacitors in an AC circuit. So let's share the PowerPoint. That's the last quiz from inductors. So capacitors in an AC circuit, we have the voltage source here, alternating voltage source. We have a capacitor, we have the current through the capacitor and the voltage across the capacitor. So applying Kirchhoff's loop rule, delta V is plus delta VC is equal to 0. Well, what is delta VC? Well, it's the charge divided by the capacitance. Delta V minus Q divided by C equals 0. And so Q, the charge, is equal to C delta C times delta V max sine omega t. Of course, Q is charge per, it's a time rate of change of charge. So I sub C is equal to dq dt, which is equal to omega c times delta V max cosine omega t. So the derivative of sine omega t is omega times cosine omega t. So cosine omega t is equal, using the identity, cosine omega t equals sine omega t plus pi over 2. We get that IC is equal to omega c times delta V max times sine omega t plus pi over 2. Here we see that the current leads the voltage by 1/4 of a cycle. The current and the voltage phases are at 90 degrees to each other. As it's rotating around, remember it's rotating around counterclockwise, the current leads the voltage. It's ahead of the voltage. Now let's look at, if we go back to the DC case of a capacitor, a charging capacitor, you have an RC circuit. You remember when you first flip the switch, there's no charge against on the capacitor, but the current is max. So the current is at a peak before the voltage even begins. Again, this is my own little memory aid. You can disregard it if it doesn't help you, but this is the way I remember it. So the current leads, the flip of the switch. On a DC case, you get max current and the voltage, the charge builds up. So we can see here that at 0 you have max current, but the voltage is going to go up to its max just as the current goes down to 0. But this is an AC case, so it keeps going back and forth. So the current and the voltage phases are out 90 degrees to each other. Okay, now capacitive reactance, IC is equal to omega C times delta V max cosine omega t. Again, we know that current is equal to the delta V divided by the resistance. The equivalent of that is Imax. Since Imax equals omega C delta V max is equal to, we take that omega C and we put it in the denominator. We have to inverse it. Delta V max is equal to 1 over omega C. So the capacitive reactance X sub C is equal to 1 over omega C. So that's 1 over 2 pi FC. So capacitive reactance X sub C is equal to 1 over omega C, which is equal to 1 over 2 pi FC. I max is equal to delta V max divided by the capacitive reactance X sub C. I RMS is equal to VRMS divided by the capacitive reactance X sub C. And delta VC equals delta V max sine omega t, which is equal to I max times X sub C sine omega t. Let's see, consider the AC circuit in the figure. The frequency of the AC source is adjusted while its voltage amplitude is held constant. When does the light bulb glow the brightest? It glows the brightest at high frequencies. It glows the brightest at low frequencies. The brightness is the same at all frequencies. Well, let's go look at our equation. Well, X sub C, as the frequency goes up, X sub C goes lower. Well, if X, so that's in this equation. If the if F increases, X sub C is lower. Well, since X sub C is lower, as the frequency goes up, Imax will increase. If the frequency goes down, X sub C increases, and Imax decreases. Let's go to the extreme point. If you go down to DC, you've got a capacitor that'll eventually charge and there'll be no current flow, right? So it glows brightest at high frequencies. And sure enough, there's the answer, the high frequencies. Okay, consider an AC circuit in the figure. The frequency of the AC source is adjusted while its voltage amplitude is held constant. When does the light bulb glow the brightest? Well, at high frequencies, the capacitor will basically become a short, and the inductor will increases in reactance. At low frequencies, this becomes, let's take it all the way to DC, this becomes an open circuit, and this just becomes basically just a piece of wire. And so the answer in this case would be, it would be B. It glows brightest at low frequencies. Okay, now next we're going to get into RLC circuits.